Alright people, welcome back to another Rock the JVM video. I'm Daniel, and in this video and in the subsequent videos, we're going to have a mini-series in which we're going to discuss some advanced type-level programming techniques in Scala. So this mini-series will assume that you're an advanced Scala programmer, and in particular very familiar and comfortable with how implicits work and implicit methods. So if you're curious about how powerful the Scala compiler is, and I'm going to break a spoiler here, it's very powerful, then this video series will be for you, and you'll probably 99% boost your Scala skills after watching this video series. As always, I will recommend that you code alongside me because the code will be quite complicated, and whenever you need to refresh your memory or get back to some of these concepts that we're going to discuss in this series, just refer back to this video, to this mini-series, or to the written versions at rockthejvm.com/blog, and you will find the links to the articles the first thing in the description of these videos. So without further ado, let's get back to the code and let me talk about what we're going to actually do in this mini-series. Now, in the first part of the mini-series, I will introduce to you the notion of values as types, and I'll show you how you can embed a mathematical problem as a type constraint, which the Scala compiler will happily validate or invalidate for you before the code can even compile. Now, this series is applicable to Scala 2. In particular, I'm working on Scala 2.12. If you're using Scala 2.13, make sure you go to build.sbt and add this org scala lang scala reflect package, which you can also find in the description of this video. So add this library definition to the library dependencies. So say library dependencies plus equals, and then say org.scalalang % scala reflect %, and then you will have the Scala version.value, and then you should be good to go. We are going to use the Scala reflect just to print some types. This is not a cheat. We aren't using reflection to manipulate types at runtime. So we are going to simply use the reflect package to print stuff to the console, and I'm going to add an import here. I'm going to say Scala reflect runtime universe and then underscore. And I'm going to write a small method to show something on the console. So I'm going to type it with a type parameter t, and I'm going to pass a value, which is a type t, but we aren't actually going to use it. We're going to use its type tag, which you can pass as an implicit value. So I'm going to pass that as an implicit argument, implicit tag of type tag. And this will simply be tag to string replace, because the string here will be very verbose, and I'm going to replace the string content, which is the name of my package here, dot type level programming dot, and I'm going to replace that with the empty string. So depending on where you put your code, you might want to change the string here just to replace your package name dot your application with the empty string, because the types that we're going to print to the console will be quite big and will be quite hard to read unless we do this small replacement. So this particular method will print the type of a value at runtime. So regardless of what kind of value you pass to it, for example, if I define a main method and I want to print line show, and I'm going to pass here a list of ints, let's say list 1, 2, 3. If I run this application, I'm going to give it a few seconds to compile. Look at the kind of string we get to the console. So we get a type tag with a list of ints. So notice that the entire type signature is being carried on to the runtime. Now, rest assured, we aren't using this reflection package and this show method to manipulate types at runtime. We're simply going to print the type information that we obtain after solving some constraint satisfaction problem that the compiler will happily solve for us. So this was the boilerplate, so to speak. All right, now with that out of the way, we are ready to dive into type level programming with Scala. So what is type level programming? Well, normal programming works with normal values, which are concrete representations of some types in memory. So we will need to allocate numbers and objects and functions and all that sort of thing. And then your program will need to process those values to obtain your desired result. And so normal programming happens at runtime, after your code is compiled and after your executable gets executed. Type-level programming, on the other hand, will involve using the compiler as a program executor. What do I mean by that? The compiler will infer some type constraints, so some relationships between types, that will mean the response to a mathematical problem or to some sort of other program. So we will program by enforcing some type constraints or some relationships between types. And so the compiler will validate the relationships between those types at compile time before our program is even run. This is why the runtime is so short, just printing something to the console. The compiler will do most of the work, as we will see shortly. Now, we're going to start easy. We're going to declare a type that will represent natural numbers. However, we aren't going to use the plain int type, but rather we will represent the relationship between numbers as a succession. So here's what I'm going to do. I'm going to define a trait called nat from naturals, and I'm going to define a class _0, which extends nat. So the class _0 is a type nat. All right. Now, we are going to represent the rest of the natural numbers by another class that I'm going to call successor, which takes a type argument, let's call this n, which derives from nat. So this is a type constraint, and this extends nat as well. So we are able to represent the natural numbers as types, not as values. So we have the type _0, the type successor of 0, the type successor of successor of 0, the type successor of successor of successor of 0, and so on and so forth, that represents a natural number, but as a type. So let me go ahead and define some type aliases. So I'm going to define a type _1 as successor of 0. This is just a type alias. I'm going to define type 2. This is a successor of 1. So this is basically a successor of 0. Let me define some more. This is a successor of 2, which is successor of successor of successor of 0. Let me put in some underscores, and I'm going to define 2 more, _4, successor of 3, and type _5 as successor of 4. So we've defined just a bunch of numbers that we can play around with. Notice that these are types, they're not values. This representation, this natural number representation, is called Peano. Peano arithmetic. From the really nice mathematician Giuseppe Peano, who would probably love Scala if he saw this kind of code, because he formalized the mathematics of natural numbers and some axioms and properties of natural numbers determined in this way. So this is the Peano representation of numbers in terms of the number 0 and the successor relationship between numbers. Notice that we cannot call, for example, type, let's call this animal for the lack of a better word, successor of, for example, int. You can't do that because int doesn't extend nat. If I try to compile this, then we would have a compiler warning. Type argument int does not conform to successor's type parameter bounds and must extend nat. All right, so you can only have successor of another natural number. All right, so I hope this is not too difficult. This first part was gentle enough. Now, if I've caught your attention and curiosity, then do stick around for the rest of this video and for the following videos, because we're in for quite a ride. Now, at this stage, we have numbers and their succession relationship as type constraints. Now, the number 1 is the successor of 0, 2 is the successor of 1, and so on and so forth. Now, we would like to be able to tell whether one number is less than another as a type relationship. So this type relationship is not trivial. We want to say whether _2 is less than _4, for example. how can we embed that as a type relationship? Succession, which is the difference of 1, this is fine. We can say that _1 is less than _2 because 2 is the successor of 1. But how can you tell that 2 is less than 4 just by looking at this type definition? Now, the answer is that for type level programming, we will make the compiler determine that for us through a type definition. So I'm going to define a trait that I'm going to call less than. So the less than sign, because the Scala is very permissive with naming methods, identifiers, and types. And so less than is just perfectly fine and very convenient. The less than will take 2 type arguments, a type A, which extends nat, and type argument B, which also extends nat. So if I said that a value, let's call this comparison, of type less than with _2 and _4, if the compiler can automatically create an instance of this type for me, then we would interpret that as the validation of the relationship between _2 and _4 less than relationship. So we will make the compiler automatically create an instance of less than 2 and 4 to validate the relationship that 2 is less than 4. Now, we will never build instances of this less than type ourselves, but we will make the compiler build implicit instances of this less than just for the right types. So we will never be able to say that 4 is less than 2. And through these implicit instances, we will therefore validate the existence of the less than relationship for various numbers and thus prove the comparison between numbers. This is all pretty complicated. So let me define some implicit methods. So I'm going to define a companion object for less than, and I'm going to define an implicit method. So implicit def, I'm going to call this less than basic, which will take a type argument b, which must be a subclass of nat. And this will return an instance of less than for 0 and successor of b. And I'll automatically build one. So I'm going to say new less than for _0 and successor of b. And I'm going to open and close some curly braces because the less than is a trait. What has this done? This implicit method will basically say that for every type argument b, which is a natural, the compiler can automatically build on demand an instance of less than between 0 and the successor of that number, which means that 0 is less than the successor of any number, which if you take a few moments to think about it, it's always true because the successor of any number is at least 1. If you take a look at these definitions here at the very top, notice that the type 1 starts with the successor of 0 and everything else is bigger than 1. And so the successor of any number is strictly bigger than 0. And so for every natural, the compiler can automatically create an instance of 0 is less than the successor of b, and we've instantiated it here. What does that mean? What does that mean for us? Let me define a small method to fetch the implicit instance that the compiler can automatically build. So I'm going to define a method called apply that for 2 type arguments, a which is a natural and b which is a natural, I'm going to return whatever the compiler can fetch as an implicit instance of less than, which is of type less than between a and b. And I'm going to return LT. This is kind of like implicitly if you've ever used it. So this apply method will fetch whatever implicit value of type a less than b that the compiler can find. And so if I write something like comparison, which is a less than between 0 and 1, and on the right hand side I will say less than applied to 0 and 1, notice that the compiler can compile my code because it was able to find an implicit instance of 0 is less than 1 given by this implicit method, because _1 is the place, takes the place of b over here, and so the compiler can build an implicit instance of less than between 0 and 1 as this implementation, which is not really that important. But the important thing is that the compiler can compile my code. So if I go to build at the very top and say recompile, then the compiler shouldn't issue any errors because it was able to find an implicit instance of 0 is less than 1. So if the code compiles, then it means that the truth value of 0 less than 1 is true. However, if I said comparison between 1 and 3 as less than between _1 and _3, the compiler cannot compile my code so far because it cannot find an implicit instance of the type _1 is less than _3. And notice it's using the infix notation, which I'm going to use here. This is basically a syntactic sugar. So if I said _1 less than _3, it's as if I said less than between _1 and _3. All right, so this particular section was a little bit more difficult than the joyful piano arithmetic that we discussed earlier. So if you're having trouble with that, pause the video and try to rewind and follow the original reasoning behind this implicit method, which makes the compiler do a little bit of work for us. All right, we're going to follow up with an additional implicit method so that we can help the compiler prove the existence of the type _1 less than _3. And just for the sake of tongue twisters, I'm not going to say underscores too much. I'm going to say 1 less than 3 because we aren't operating with values, we're operating with types. So I'm going to say we are going to help the compiler validate the instance of the type 1 less than 3. All right, so I'm going to define another implicit method, and I'm going to name this inductive, because this is basically an inductive mathematical proof that the compiler will need to go through. And this inductive method will take two type arguments, a which is a nat, and b which is a nat. And this will require an existing implicit instance of less than, which is of type less than between a and b. And if the compiler can find an implicit instance of a less than b, then the compiler will automatically create an instance of less than between successor a and successor b. And I'm going to simply create a new instance of that trait between successor a and successor b, and open and close some curly braces. So this implicit method is probably the crux of the theorem prover. And notice that after I've written this method, the compiler is able to validate my code. This is interesting. So when I write something like this, less than between 1 and 3, the compiler will try to call the apply method. And so the compiler will try to find an implicit instance of 1 less than 3. So I'm going to run you through the operations that the compiler will have to do to validate my code. So I'm going to call the apply method between 1 and 3. Well, this requires an implicit less than of 1 and 3. Well, in this case, the compiler can run the inductive method and require an implicit instance of less than between 0 and 2. So the compiler will run inductive between _1 and _3, which requires implicit less than instance between 0 and 2. So if you take a look at the signature of the inductive method, if the compiler had an instance of 0 less than 2, then the compiler is able to construct an instance of successor 0 less than successor 2, or namely 1 less than 3. Now, in this case, an instance of 0 less than 2 can be built with the method ltbasic. So ltbasic, and the type here must be a type b such that the return type is less than 0 and successor b. And the required type for me is 0 less than 2, and 2 is a successor of 1. And so the type parameter b is inferred by the compiler to be _1. So ltbasic with _1 produces an implicit instance between _0 and successor of 1, which is the same as an instance between 0 and 2. Okay, so after calling LT_basic, the compiler is able to produce an implicit instance of 0 less than 2, which is then used in the inductive step to create the implicit 1 less than 3, which is then used to the apply method. And so this particular construction is applicable to us, and the code can compile. And in main, if you were to print the show representation of this comparison, then not only will the code compile, but you'll also see its runtime type, which is type tag of _1 is less than _3. If this type exists, if the compiler can automatically build an instance of this type, then the type relationship between 1 and 3 is validated. Conversely, if the code cannot compile, then it's not true, then two numbers are less in the less than or equal relationship. So if I wrote, let's call this invalid comparison, which bears the type, for example, _3 less than _2, you can use the type, but you cannot use the apply method because the compiler cannot automatically build an instance for you. So if I were to write less than between 3 and 2, notice that the compiler cannot compile my code because it says no implicits found for parameter less than of type 3 less than 2. That means that 3 is not less than 2. And notice how this type relationship is validated by the compiler before you even touch the build button. All right, so this is very, very powerful. I'm going to comment this out and I'm going to say will not compile. 3 is not less than 2. All right, awesome. So I hope this makes sense. I'm going to shamelessly copy the less than definition here, and I'm going to duplicate the code into a less than or equal trait and companion object. I'm going to name this implicit method LTE for less than or equal, and I'm going to simply remove the method signatures at the very end, and I'm going to keep the apply method, and I'm going to have it receive an implicit LTE of type less than or equal between A and B, and return that particular instance that the compiler can automatically infer. And if you're brave enough, I would invite you to pause the video and try to implement these two methods in the same style that I wrote above for the less than relationship. Now I'm going to carry on with the implementation of less than or equal. And for less than or equal basic, the first implicit def, it is true that for every type B, which is a natural, the type 0 will be less than or equal to it because 0 is the minimum natural number. So this method will return an instance of less than or equal between 0 and that type B. And I'm going to simply create one. I'm going to say new less than or equal with type 0 and B, and I'm going to leave it blank. Now, the inductive implicit def will be very similar to that for less than. So for both types A and B, if the compiler can find an implicit less than or equal which is of type less than or equal between A and B, the compiler will automatically be able to construct an instance of less than or equal between successor A and successor B. And I'm going to simply create one. So I'm going to say new less than or equal between successor A and successor B with an empty implementation. And just as was the case with the less than relationship, we can validate the existence of a type. So I'm going to say val, let's say less than or equal test of type _1 less than or equal to _1, for example. And I'm going to simply call the apply method of the less than or equal type. So I'm going to say less than or equal with the type _1 and _1, and the compiler should automatically validate this type because 1 is less than or equal to 1. Conversely, if I wanted to create an invalid comparison, let's call this invalid LTE of type, let's say 3 less than or equal to 1, as the apply method of less than or equal between 3 and 1, the compiler will not be able to validate this because it cannot build an implicit instance of 3 less than or equal to 1. So I'm going to comment this out. I'm going to say will not compile. All right, so less than or equal will work in just the same fashion as less than. All right, so this was a pretty hard video. All right, so this one was pretty tough, and I really appreciate that you've stayed along so far. Stick around to Rock the JVM for the follow-up videos to this one, where I'm going to show you even more complicated problems that the compiler can solve automatically with type-level programming. In the meantime, go ahead and follow Rock the JVM on Twitter and LinkedIn and Facebook. Read the article of this video at rockthejvm.com/blog, and very importantly, click the like button for me and subscribe to the Rock the JVM channels for more videos like this. I'm dying for feedback, so leave your comments in the video below. And until next time, I'm Daniel for Rock the JVM, signing off.